Hi, Helicopter Flying Handbook, Chapter 2, Aerodynamics of Flight, page 13 of 28. We're going to go into powered flight. Powered flight. In powered flight, hovering vertical, forward, sideward, or rearward, the total lift and thrust forces of a rotor are perpendicular to the tip path, plane, or plane of rotation of the rotor. Hovering flight. Hovering is the most challenging part of flying a helicopter. This is because a helicopter generates its own gusty air while in a hover, which acts against the fuselage and flight control surfaces. The end result is constant control inputs and corrections by the pilot to keep the helicopter where it is required to be. Despite the complexity of the task, the control inputs in a hover are simple. The cyclic is used to eliminate drift in the horizontal plane, controlling forward, backward, right, and left movement of travel. The throttle, if not governed control, is used to control revolutions per minute, RPM. The collective is used to maintain altitude. The pedals are used to control nose direction or heading. It is the interaction of these controls that makes hovering difficult. Since an adjustment in any one control requires an adjustment in the other two, creating a cycle of constant correction. During hovering flight, a helicopter maintains a constant position over a selected point, usually a few feet above the ground. The ability of the helicopter to hover comes from both the lift component, which is the force developed by the main rotors to overcome gravity and aircraft weight, and the thrust component, which acts horizontally to accelerate or decelerate the helicopter in a desired direction. Pilots direct the thrust of the rotor system by using the cyclic to change the tip path plane as compared to the visible horizon to induce travel or compensate for the wind and hold a position. At a hover and no wind condition, all opposing forces, lift, thrust, drag, and weight are in balance. They are equal and opposite. Therefore, lift and weight are equal, resulting in a helicopter remaining in a stationary hover. To maintain a hover at a constant altitude, the lift must equal the weight of the helicopter. Thrust must equal any wind and tail rotor thrust to maintain position. The power must be sufficient to turn the rotors and overcome the various drags and frictions involved. While hovering, the amount of the main rotor thrust can be changed to maintain the desired hovering altitude. This is done by changing the angle of incidence by moving the collective of the rotor blades and hence the angle of attack of the main rotor blades. Changing the angle of attack changes the drag on the rotor blades, and the power delivered by the engine must change as well to keep the rotor speed constant. The weight that must be supported is the total weight of the helicopter and its occupants. If the amount of the lift is greater than the actual weight, the helicopter accelerates upward until the lift force is equal to the weight gain altitude. If thrust is less than weight, the helicopter accelerates downward. When operating near the ground, the effects of the proximity to the surface change this response. The drag of the hovering helicopter is mainly induced drag incurred while the blades are producing lift. There is, however, some profile drag on the blades as they rotate through the air and small amount of parasite drag from the non-lift producing surfaces of the helicopter, such as the rotor hub, the cowlings, and the landing gear. Throughout the rest of this discussion, the term drag includes induced profile and parasite drag. An important consequence of producing thrust is torque. As discussed in Chapter 2, Newton's third law, for every action there is an equal and opposite reaction. Therefore, as engine turns the main rotor system in a counterclockwise direction, the helicopter fuselage wants to turn clockwise. The amount of torque is directly related to the amount of engine power being used to turn the main rotor systems. Remember, as power changes, torque changes. To counteract this torque-induced turning tendency, an anti-torque rotor or tail rotor is incorporated into most helicopter designs. A pilot can vary the amount of thrust produced by the tail rotor in relation to the amount of torque produced by the engine. As the engine supplies more power to the main rotor, the tail rotor must produce more thrust to overcome the increased torque effect. This control change is accomplished through the use of anti-torque pedals. Translating tendency, drift. During hovering flight, a single main rotor helicopter tends to move in a direction of tail rotor thrust. This lateral sideward movement is called translating tendency. The tail rotor is designed to produce thrust in a direction opposite the torque. The thrust produced by the tail rotor is sufficient to move the helicopter laterally. Blade rotation counterclockwise. Alright, so you want to drift right. Yes. To counteract this tendency, one or more of the following features may be used. All examples are for counterclockwise rotating main rotor systems. The main transmission is mounted at a slight angle to the left, when viewed from behind, so that the rotor mast has a built-in tilt to opposite the tail rotor thrust. Flight controls can be rigged so that the rotor disc is tilted to the left slightly when the cyclic is centered. Whichever method is used, the tip path plane is tilted slightly to the left in a hover. If the transmission is mounted so the rotor shaft is vertical with respect to the fuselage, the helicopter hangs left skid low in the hover. The opposite is true for the rotor systems turning clockwise when viewed from above. The helicopter fuselage would also be tilted when the tail rotor is below the main rotor disc and supply an anti-torque thrust. The fuselage tilt is caused by the imperfect balance of the tail rotor thrust against the main rotor torque in the same plane. The helicopter tilts due to two separate forces. The main rotor disc tilts to neutralize the translating tendency and a lower tail rotor thrust below the plane of the torque action. In forward flight, the tail rotor continues to push to the right, and the helicopter makes a small angle with the wind when the rotors are level and the slip ball is in the middle. This is called inherent side slip. For some larger helicopters, the vertical fin or stabilizer is often designed with the tail rotor mounted on them to correct this side slip and eliminate some of the tilting at a hover. Also, by mounting a tail rotor on top of the vertical fin or pylon, the anti-torque is more in line with or closer to the horizontal plane of the torque, resulting in less airframe or body lean from the tail rotor. Having the tail rotor higher off the ground reduces the risk of objects coming in contact with the blades, but at the cost of increased weight and complexity. Perpendicular action. Since the fuselage of the helicopter with a single main rotor is suspended from a single point at a considerable mass, it is free to oscillate either longitudinally or laterally in the same way as a pendulum. This pendular action can be exaggerated by over-controlling. Therefore, control movement should be smooth and not exaggerated. The horizontal stabilizer tends to level the airframe in forward flight. However, in a rearward flight, the horizontal stabilizer can press the tail downward, resulting in a tail strike if the helicopter is moved into the wind. Normally, with the helicopter mostly into the wind, the horizontal stabilizer experiences less headwind component as the helicopter begins rearward travel downwind. When the rearward flight ground speed equals the wind speed, the helicopter is merely hovering in a no-wind condition. However, rearward hovering into the wind requires considerable care and caution to prevent tail strikes. Yes. Alright, we'll go into coning right here. Yep, coning. In order for a helicopter to generate lift, the rotor blades must be turning. Rotor system's rotation drives the blades into the air, creating relative wind component without having to move the airframe through the air as with an airplane or a glider. Depending on the motion of the blades in the helicopter airframe, many factors cause the relative wind direction to vary. The rotation of the rotor system creates centrifugal force, inertia, which tends to pull the blades straight outward from the main rotor hub. The faster the rotation is, the greater the centrifugal force, and the slower the rotation is, the smaller the centrifugal force. This force gives the rotor blades their rigidity and, in turn, the strength to support the weight of the helicopter. The maximum centrifugal force generated is determined by the maximum operating rotor revolutions per minute, the rotations per minute. As lift on the blades is increased in a takeoff, for example, two major forces are acting at the same time. Centrifugal forces acting outward and lift acting upward. The result of these two forces is that the blades assume a conical path instead of remaining in the plane perpendicular to the mast. This can be seen in any helicopter when it takes off. The rotor disc changes from flat to a slight cone shape. If the rotor RPM is allowed to go too low, below the minimum power on a rotor RPM, for example, the centrifugal force becomes smaller and the coning angle becomes much larger. In other words, should the RPM decrease too much, at some point the rotor blades fold up with no chance in recovery. During takeoff, the combination of centrifugal force and lift can cause the rotor disc to cone upwards. The Coriolis Effect, the law of conservation of angular momentum. The Coriolis Effect is also referred to as the law of conservation of angular momentum. It states that the value of angular momentum of a rotating body does not change unless an external force is applied. In other words, a rotating body continues to rotate with the same rotational velocity until some external force is applied to change the speed of rotation. Angular momentum is the moment of inertia, mass times distance from the center of rotation squared, multiplied by the speed of rotation. Angular momentum is the moment of inertia, the mass times distance from the center of rotation squared, multiplied by the speed of rotation. Changes in the angular velocity, known as angular acceleration and deceleration, take place as the mass of a rotating body is moved closer to or farther away from the axis of rotation. The speed of the rotating mass varies proportionally with the square of the radius. An excellent example of this principle in action is a figure skater performing a spin on ice skates. The skater begins rotation on one foot with the other leg and both arms extended. The rotation of the skater's body is relatively slow. When a skater draws both arms and one leg inward, the moment of inertia, mass times radius squared, becomes much smaller and the body is rotating almost faster than the eye can follow, because the angular momentum must, by law of nature, remain the same. No external force applied. The angular velocity must increase. The rotor blade rotating about the rotor hub possesses angular momentum. As the rotor begins to cone during the G-loading maneuvers, the diameter of the rotor disc shrinks due to conservation of angular momentum. The blades continue to travel the same speed, even though the blade tips have a shorter distance to travel due to the reduced disc diameter. The action results in an increase in rotor RPM, which causes a slight increase in lift. Most pilots arrest this increase of RPM with an increase in collective pitch. This increase in blade RPM lift is somewhat negated by the slightly smaller disc area as the blades cone upwards. So we'll stop there on page 16 of 28, but page 15 of 28 we were just going over pretty much the coning and inertia and the torque and blades flexing and coning, and the tilt. All right, so we'll stop there on page 16 of 28. All right, check you later.